Hey folks, I got a brief video on temperature dependence of resistors. Now, for most resistors, especially ones that are made of metallic substances, as you increase temperature, their resistance goes up. And the main reason for that is you can imagine that the metal is chock full of electrons, and then you are an electron trying to get through all the other electrons. Well, as you increase the temperature, all the other electrons are going to bump around faster because all temperature is the average kinetic energy of the atoms and including the electrons of the substance. So if you increase temperature, electrons move around more, and you trying to get through the resistor makes it tougher. So imagine a classroom and you're trying to walk from one end to the other. If the students are all sitting still, it's pretty easy to do. If the students are all moving around, it's going to be harder for you to get across the room. Now, some substances, their resistance actually goes down with temperature. So an example is carbon. So it turns out that the effect of increasing temperature, the effect of the more electrons moving around, making it hard to get through, is less than the effect of the increased temperature, making it easier for electrons to be knocked off the carbon atom. So there's a chart of this here. So this far right column tells you how resistance changes with temperature. So for instance, for all of these things here, the resistance goes up with temperature. But if you look at carbon and a couple other things, resistance actually goes down with temperature. So I got one example problem to kind of do with you, and we'll talk about the equation. So it turns out that resistivity, okay, is equal to some base value at 20 degrees Celsius, that's room temperature. And then the rest of the equation is 1 plus alpha, that is your temperature coefficient. So in this chart here, that's this number on the far right there, times T minus T naught. Those are temperatures, and those are in degrees Celsius. And by the way, T naught is defined as 20 degrees Celsius. Okay, so for T naught, you can always put 20 in. And again, that's roughly room temperature. Now, because resistance equals rho L over A, we can say resistance overall also depends on this. It would be some set value, and then you'd have the same exact coefficient in there. Okay, same exact stuff in the bracket. So for an example, you might know that iron and carbon have vastly different resistances. Carbon has a lot more resistance than iron does. If you look at our chart here, iron is 10 to the negative 8th. Carbon is 3.5 times 10 to the negative 5th. That's a lot more resistance. It's factors of 10 more resistance, okay? But if I heat them up, iron's resistance goes up and carbon's resistance goes down. Is there a temperature that where you can heat them both up to the same temperature or to a higher temperature and they'll have the same resistance? So is there a temperature where equal sizes, equal geometries of iron and copper could have the same resistance? So what we're going to say is if the length and area of both chunks of material are the same, we're going to ignore that. We're just going to look at the resistivity. Is there a temperature at which the resistivity is the same for both copper and iron? Okay, or not copper and iron, sorry, carbon and iron. So we're going to set the resistivity of iron equal to the resistivity of carbon. Okay, so you're going to have rho naught for iron. So the left side of this will be iron, and then you're going to have your 1 plus your alpha times T minus 20. That's your or temperature naught. That's going to be for iron. Is there a temperature at which the resistivity, this will be iron there and iron here. For rho naught for carbon, okay, and then 1 plus the alpha of carbon times T minus 20. Is there a temperature at which these two will have an equal resistivity and therefore equal resistance? So all we got to do is look these values up in our chart. So rho naught for iron is 10 times 10 to the negative 8th approximately. So this becomes 10 times 10 to the negative 8th. And then you've got 1 plus alpha for iron is right there. That's 5 times 10 to the, let's see, 5 times 10 is a negative third. Like so. And then T minus 20. Is there a place where that'll equal carbon? Now, carbon's rho naught is down here, 3.5 times 10 to the negative fifth. And then 1 plus an alpha for carbon is negative 0.5 times 10 to the negative third. So negative 0.5 times 10 to the negative third, and then T minus 20. So if you very carefully plug all this stuff in and solve for T, all right, here's what I got. I got a temperature of about 1959 degrees Celsius. Okay, you can double check my calculation there, but that's what I got. Now, so that's the temperature at which carbon and iron would have the same resistance. Now, could we actually do this? No, I think iron is at this point molten at that point. So you couldn't actually have two solid pieces, one of iron and one of carbon, and make them have the same resistance. The iron would melt before you ever reach that temperature. But it's a good exercise to see, could you do it, and using this equation. All right, so again, that's a brief example and explanation as to why resistance changes with temperature. I hope that example was helpful, and thank you very much.